analysis. Directly it is given that using mesh analysis you have to solve. So you have to identify the number of meshes. We have already done how to identify, how to verify the number of meshes. Those things we have already done. Okay. So what is the problem here? Mesh 1, mesh 2, mesh 3. Clockwise direction, let us say some unknown currents, I1, I2, I3. Then write the KVL equation for each of the mesh. Okay. You can solve the equation. You will get three equations, three unknown quantities, I1 and I1, I2, I3. You'll be able to solve. Again, this is another, there are two mesh 1 and mesh 2. Okay. So I think you'll be able to solve these problems. It doesn't require any other knowledge. Here already I1, I2, I3 is given. So just apply mesh analysis. Most of the things you have to apply mesh analysis. At the end, there is another one problem. Here you can apply the nodal analysis. Okay. Still, there is no like hard and fast rule that where you have to apply nodal and mesh analysis. Today, I will just give you a guideline, like how to choose that whether you have to use nodal or mesh analysis. But that is only a guideline. Definitely, you can apply them according to your choice. If but in some cases, you may require to do more calculus. That is the one. How to identify that thing that I will discuss today. So I don't think for doing these problems, you will require to see any other theory, new concepts, anything. Whatever has been done in class, that will be required. Okay, 7 questions, 1 week time. Each day, if you solve one question, it will be over. Okay, and I don't. It's not that you have to give the correct answer. That is not required. Have you tried it? If you have tried, whether that's the same things that was taught in class, have you followed those things? You can do any other thing, any other way. Okay, that is not the problem. But the answer should be correct. Even if the answer is not correct, if you have tried, genuinely, if you have tried, if you're not copied from somewhere, you'll be marked according to that. Okay, so submit before the deadline. Okay, that is the only. Yes. Okay, let me just start the recording.
Recording in progress.
Yes. Okay. So now we have done the mesh analysis, mesh, or you can write it loop mesh. Let us write it as mesh. Okay. So the main question that should come to your mind, like when to apply mesh analysis, when to apply loop, nodal analysis, mesh and nodal analysis. Okay. That is the main question. So how to identify whether to apply mesh or nodal? The main aim is to simplify your like calculus. Okay. You have to choose that method by which the calculation will be easier. There is no hard and fast rule. You can always apply. If it was suited for applying mesh, if you are applying nodal analysis, then the number of equations will increase. Okay, but you can get the correct answer still. So see how, just see this first point, that mesh analysis is generally used for circuits having many series connected elements. Okay, if in a circuit you are seeing that okay, the number of elements that are connected in series. Okay, series connection. By series connection, I mean
Wow.
okay. I was trying to find something to write with. I don't have the writing pad. Okay. But if in a circuit there are a number of series connected elements, then you have to apply mesh analysis. Because in mesh analysis, if you remember, you are using KVL. Now, while applying KVL, you can, if you remember, applying KVL, you are going in clockwise direction, and all the elements are connected in series. Okay, if in a circuit more number of series connected elements are there, then it is better to apply mesh analysis. Okay, nodal analysis is more suitable of the circuit having parallel connected elements. If you remember, okay, so if there are more parallel connected elements, then you have to apply nodal analysis. If you don't do that, it's also fine. Okay. The main factor in selection is the number of equations. That means the idea is to, so that you get minimum number of equations, minimum number of unknowns. Okay, so that your calculations become easier. Okay. Yeah. So that is the main idea. So these 3 points are the most important. That if in a circuit more number of series connected elements are there, okay, then you have to apply mesh analysis. If there are more parallel connected elements, then you have to apply nodal analysis. Okay, and now if there is a question that, okay, if you have to find out what is the current that is flowing in a particular loop or a mesh, then you apply mesh analysis, no problem. If the question is asked that you have to find the voltage at a particular node, then you can apply nodal analysis. But using mesh analysis also, you can find out the nodal voltage. Using nodal analysis also, you can find the current in a particular mesh. Okay, so there is no hard and fast rule. It is just a guideline. So that with this discussion, I want to conclude our discussion on mesh and nodal analysis. The video lectures, all the problems that we have discussed, all the possible cases. Okay, and the most important cases are the super mesh and super node. So those things I have already shared with you, and the video recordings that I had, I have already shared with you. Okay. Next, we'll move to some basic small theorems. Before going into the important theorems, I will discuss a small topic that is known as source transformation. Okay, it is very important, but it is also intuitive based on what we have already studied. Okay, what is source transformation? Basically, source, you have already know what are the different kinds of sources, dependent and independent. If you talk about independent, there are 2 kinds: constant voltage, constant current source. They can be ideal, they can be practical. But since it's a basic course, we will mainly concentrate on ideal sources. Okay, ideal current source, ideal voltage source. If that is the case, then this topic gives you an idea that if there is a voltage source, how you can convert it or represent it in terms of a current source. If there is a current source, how you can represent it in terms of voltage source. The reason is why we need to do that, because it makes sometimes the circuit analysis becomes easier. If you do this, sometimes the circuit analysis becomes easier. Now, for source transformation, there are 4 rules. You have to remember these rules. Rule 1, rule 2, rule 3, and rule 4. If you remember these 4 rules, then source transformation becomes very easy. Yeah. Transformation means like several voltage or like several voltage source or current source you can represent using a single one. Like for example, rule 1, if there are several voltage sources that are connected in series, okay, like V1, V2, V3, V4 till Vn, let us say. Okay, so these voltage sources plus minus sign are there, they are connected in series, so they can be equivalently represented as, instead of like if there are 2 resistors in series, how you represent? You just sum them up. If there are 2 resistances in parallel, what is the equivalent resistance? You know how to find the equivalent resistance if they are connected in parallel. If the 2 resistors are connected in series, you know how to find the equivalent resistance. Similarly, if n voltage sources are connected in series, then the equivalent voltage source will be, just you have to add. You have to add V1 plus V2 plus Vn. Okay, if the polarity are opposite, let us say in V1, this positive sign is on the this towards the top, and the negative sign is towards the bottom. Similarly, if V2 is towards the top, the plus sign is towards the top, the minus sign is towards the bottom. But if it's the other way around, if V1 stays like this, and in V2 the plus sign is towards the bottom and the minus sign goes to the top, then they are opposing each other. V1 and V2 is opposing each other. Then it will V1 minus V2 or V2 minus V1, depending on which one is greater. Okay, but you can add them based on the polarity. Their sign may change. This plus sign may become minus sign if they are connected in opposite direction. The polarity is opposite, but the basic thing you have to add. Similarly, if there are n current sources that are connected in parallel, then the equivalent current source will be their addition. If current sources are the n number of current sources are connected in parallel, then you add them. That will be the equivalent current source. Because here through this part I1 is flowing, through this part I2 is flowing, through this part IN is flowing. So if you see how much current is entering this particular node, let us say in KCL, we are only seeing how much current is entering. Okay, then how much current is entering? I1 plus I2 plus IN. So that will be the net current that will be at this point. That's why we are adding. Okay. Similarly, if you apply this KVL here, okay, if you go in clockwise direction, then you are encountering the minus sign first, so minus Vn, encountering the minus sign of V2 first, so minus V2, encountering the negative sign of V1 plus minus V1. So you are adding. Okay, again, you can take the minus common. So it will be V1 plus V2 plus Vn based on whether you are going in clockwise direction or anti-clockwise direction. But they will be added. If they are in same polarity, the direction of the polarity of the battery is same, they will be added, simply added. If they are opposite, they will be the minus sign will be. Is it clear? The first rule, is it clear? If you have any doubt, please let me know. The first rule of source transformation, is it clear to you or not? You have already done this while solving simple circuits. Also, you have done this. Okay, but just a formal way of knowing what is source transformation. Yes. Then rule 2. Now, in the rule 1, the voltage sources were connected in series. The current sources were connected in parallel. Okay. Now, what if voltage sources are connected in parallel and the current sources are connected in series? What will happen? So, this type of connection, it's better. It's always advised to avoid this type of connection because it may lead to the some kind of like means some of the elements will be damaged by it. Okay. Reason. Again, what is the reason? Now let us see if this current source is there. Okay, the value of the current for the first source is I1, for the second source is I2. So let us say I1 is less. I1 is less than I2. Okay, so what will be the aim of this I1? Again, these are independent constant current source. We are taking ideal sources. So it is a independent constant current source. Okay, ideal. So that means the aim of this current source will be to so that the current I flows through its terminal, I1, sorry, current I1 flows through its terminal and the direction is given. Let us say I2 is very large. I2 is very large than I1. Let us say I1 is 10 ampere and I2 is, let us say, 10,000 ampere. Okay, then what will be the aim of I2? So that 10,000 ampere flows through this terminal. But if this 10,000 ampere flows through this this current source, I1 current source, whose like capacity is to produce like 10 ampere, then definitely the internal circuits will be damaged. So some of the current source will get damaged if you connect like these current sources in parallel. The same goes here. Okay, if V1, let us say V1 has some value, let us say 5 volt, and V2 is let us say 10,000 volts, then what will happen? This side will be more positive than this one. Here you are giving 10,000 volt, and here you are giving 5 volt. Then what is the difference between these two terminals? These two terminals, it will be 10,000 minus 5, huge potential difference, so huge amount of, and there is no resistance, so huge amount of current just sorted. You have sorted, and you are giving potential difference and huge potential difference. So current will flow from this V2 to V1, and V1 may not be like V1 the resistance of ideal voltage source is almost zero. Okay, so if huge amount of current flows through it, the heat will be produced. Okay, we'll see what is heat later, how much heat may be produced, and this V1 will get damaged. Similar to this series connected current source. So this type of connection, that means voltage source in parallel and current source in series, it is not advisable. You cannot connect like this, because some of the components, some of the sources will be damaged, some of the circuitry will be damaged. Is it clear? Is it clear? The reason is very important. Like V2 is 10,000 volt, V1 is 5 volt, let us say. Then 10,000 minus 5, that is the potential difference. So current will flow in this direction. Current will flow from V1 to V2. Current flows from higher potential to lower potential. And there is no resistance which can absorb that amount of power that is being delivered. So all the power will be dissipated across this V1. Okay, whatever small resistance is there, ideally it should have zero resistance, but it has some finite amount of resistance. So V1 will be damaged. Is it clear? Let me know in the chat. The rule 2, is it clear?
Yes.
Rule 2 of the source transformation, is it clear? Let me know.
Yes, sir, it is clear.
Okay. So this is rule 2, rule 1, and then rule 2. Rule 3. Okay, this I've already told you. This part I've already told you, but it is like a formal way of saying, okay, what is the main concept of source transformation. There is a voltage source. Okay, ideal voltage source, what is the resistance? Okay, zero resistance. Okay, and there is a resistance connected across it, and resistance is connected in parallel to the voltage. Resistance is connected in parallel to the voltage. Similarly, there is current source, and a resistance is connected in series with the current. So, what is the use of this resistance? Will this resistance come into the picture? Because what is the concept of an ideal voltage source? Ideal voltage source will always try to maintain that amount of voltage V. Let us say this is V. Forget about T. T will come later when we'll discuss about AC circuits or AC sources, then T will come. Here consider as V. It is a DC battery, let us. Okay, so its aim is to maintain these V volts across its two terminals. Okay, so it will maintain this V volt across these two terminals. It will, and these two terminals are also same. Okay, this terminal and this terminal, in between there are no elements. There are no elements. So definitely here also V volts will be applied. If that is the case, then what is the use of this R? Because your circuit, whatever you will be connecting, that will be connected across these two terminals, this terminal, this terminal. If the same voltage is being applied here, and then R will be of no use, because the same voltage will be applied to this terminal, which is of your interest, because you will be applying your own circuitry that needs any kind of voltage that will be connected across this. But the same, this independent voltage source, by its very nature, it will maintain the same voltage across this terminal and this terminal, same voltage V. Then this resistance will not come into picture. Okay, so instead of that, you can remove the resistance, because resistance is of no use. Similarly here, what is the main idea of a independent current source, ideal independent current source? It will always maintain current I across this terminal. And if you connect a resistance in series, so the same current I will flow. The same current I will flow. The same current I will be flowing through these two, these two terminals. Now you will connect your own circuit in these two terminals. But irrespective of the resistance I, the same current will be flowing through your terminal. So this current as this resistance R is of no use. The resistance R is of no use. So you can remove the resistance. So the main idea, when there is a resistance connected in parallel to the voltage source, you may remove, you may neglect the resistance. If there is a resistance connected in series with the current source, you may neglect the resistance. Okay. Let me know if you have any doubt in this part. So these 4 rules you will apply at a time to simplify your circuit. Okay. Yeah. Let me know if you have any doubt in rule 3. Rule 4. Rule 4, now this is the most important one. That means how you can move from a voltage source to current source to voltage source. Now, if there is a voltage source here, in the previous rule, you cannot connect a resistance in parallel to the voltage source, but you can always connect a resistance in series with the voltage source. Similarly, in the previous rule, you cannot connect a resistance in series with the current source, but you can always connect a resistance in parallel to the current source. Now, if this is given, let us say a circuit with a particular voltage, particular battery, let us say DC source, and a particular resistance is given to you, can you write it in terms of a current source? That is the meaning. Or if a current source is given to you and a resistance is connected in parallel with it, can you represent that circuit in terms of a voltage source? Okay, the reason is that sometimes this kind of a transformation makes your circuit very easy to analyze. That means here from series connection you are moving to parallel connection. Here from parallel connection you are moving to series connection. That means you can go from this to this, voltage to current, current to voltage. Okay. Now how to do that? Simple. That means what is the current that will be flowing? Okay. Let us consider that this you are just sorting. Okay. This one you are sorting. These two terminals you are sorting. Then what is the current that will be flowing through this part? Simple. There is a voltage source and there is a resistance. Simple, using Ohm's law, you can find out what is the current. V equal to IR, I equal to V by R. Okay. From this, it is like this is like a simple, like there is a voltage source plus minus and there is a resistance. This is V, this is R. So definitely the current that will be flowing through this will be I equal to V by R. So to apply now source transformation, what you have to do? This value of I you have to represent in terms of a current source, and this resistance that was connected in series with the voltage source that will come in parallel to the current source. As simple as that. If there is a voltage source and a resistance is connected in series with that voltage source, if you want to transform that into like a current source, then you have to find out what will be the current flowing. If V amount of voltage was being applied to this resistance R, then how much current would have flowed? That is, I is equal to V by R, the same amount of current source you are writing here. And the resistance, definitely you cannot connect the resistance in series with this current source. From rule 3, you can conclude that instead of writing the resistance here, the resistance will be connected in parallel to the current source. Okay. Now, if we have to move from the current source to the voltage source. Then what you have to do, you have to find out what is the voltage across this terminal or what is the voltage across this terminal. Again, we know V equal to IR. So V will be equal to I. What is I? I is nothing but the current supplied by the source multiplied by the resistance R. So this much amount of voltage source you have to use here. And the resistance definitely, the resistance were connected in parallel to the current source. That can be done, but resistance cannot be connected in series with the voltage source. Sorry, resistance cannot be connected in parallel to the voltage source. That's why this resistance will be connected in series with the voltage. The reason we have already seen why. So is it clear? Going from voltage source to current source to voltage source. Is it clear?
Yes, sir.
Okay. So source transformation was there. It is like a basic analysis tool or the tool to simplify your circuit. Now we will move to network theorems. We will be using these concepts. Okay. You may also solve the problem without using source transformation, but if you know source transformation, you can apply that and simplify your circuit. That's the main. We will see some examples for source transformation, but along with some other theorems. Okay. Next is the first network theorem. Okay. The first network theorems will be two things. First two, that will be Thevenin's and Norton's. Thevenin's theorem and Norton's theorem. This one. Thevenin's theorem and Norton's theorem. These are two very important theorems that will simplify your analysis of complex circuits. In complex circuits, there are many elements. Okay. So how to simplify the analysis? How to simplify the analysis? For example, let us say your house wiring system. In your house, there are different kinds of wire in different rooms. There are various phases that are there. And nowadays, there are various phases so that if some kind of short circuit happens in a particular phase or a particular room, let us say, it will not affect your electricity supply in the other room. So various phases are there. So it's a complex circuit. The house wiring system is itself a whole subject. How it is done. A small experiment you will see here of house wiring system. But as an end user, what you are interested in? You are interested in whether a particular fan is being correctly operating or not, whether a particular bulb that is acting or a particular like a television that is functioning or not, that whether that is getting a power supply or not. You are not interested as the end user. You are not interested in all these circuitry. That circuitry has been done by some kind of an engineer. Okay. So here, this Thevenin's and Norton theorems makes the life of end user very easy. Okay, it simplifies the work of the end user. For example, let us say there is a very complex circuit. Let us say this is the house wiring system. House wiring system. And what you need? You need something to connect your fan. your fan needs to be connected. Now for fan, you have to apply some amount of energy or voltage. So let us say these are the two terminals of the fan. So these terminals will be connected to the output of whatever house circuitry you have. So as a end user, you are interested, okay, what is the voltage being supplied to the fan? What is the current that is flowing through the fan? What is the power that is dissipated? These are the things that you are interested in. So if you're interested only these two terminals of the fan, then why you will analyze all this complex circuitry? To alleviate this problem, this Norton and Thevenin's theorem comes into the picture. For example, this. So now this is some kind of a complex circuit, and the fan that I am talking about, the fan, the bulb, these in technical terms are known as load. Okay, how much load is there? How much energy is being generated? How much energy is being supplied? And what is the load that in a particular area is there? How much load is there? That means the fan that you are connecting, or the bulb that you are connecting, or the television that you are connecting, those are the examples of load. You are loading the system that is supplying you electricity. So, what is the procedure? There is a step-by-step procedure for solving the Thevenin's theorem. So, from this complex network, we'll go into this one. That means all this complex network will convert into a voltage source, and there will be a resistance that is connected in series. So, whatever be the complex circuitry, we will try to denote it in terms of independent voltage source and also the resistance value. And the load will be there. RL is decided by you or the end user, how much load he wants to connect. Okay. So best. Okay. So the main aim here is to find out what is the VTH, that is also known as Thevenin's equivalent voltage. RTH, this is also known as Thevenin's equivalent resistance. That is VTH and the resistor RTH. Okay. 1 minute, please. Yes. Yeah, sorry for the interruption. Am I audible? Someone please let me know. I have to change. Yeah. Please let me know, am I audible or not? Someone please let me know whether am I audible or not.
Sir, you are audible.
Yes, sir, you are audible.
Hello.
Yes, sir, you are audible.
Yes, sir, you are audible.
Okay. Simplify a complex circuit and represent it in terms of two things. One voltage and the other is a current source. Okay. Now, next, what is the procedure for that? Given a complex circuit, what is the procedure for getting the Thevenin's equivalent circuit? Okay. Let us say this one. Okay. So what is your load resistance? This is your RL. This is your RL. That is, RL will be equal to, let us say, 2 ohm. Sorry. RL is equal to 2 ohm. Okay. That means, let us say, this is the resistance of, let us say, the ceiling fan that you want to operate, or the bulb, okay, that you want to operate. So that is the, so as an end user, you are interested in how much voltage will be produced across this load, RL, okay, or how much current will be flowing through this load. This is the two things. Let us say, if you know the voltage and current across this load, then you can also find out like what is the power dissipated. Okay, so the basic thing, you have to know what is the voltage across this load and what is the current flowing. Okay, and these circuits are there, like the house wiring system. There are other loads. There may be happening. All these things are there, but you are interested in what is the voltage across this load, or Vx. Vx is the voltage across this two. Need to do all these things. You don't need to apply all the circuits and everything. You need a simplified circuit. So the aim, the output of this Thevenin's theorem will be like, at the end, what you will get? You will get this kind of a circuit. That means this load is already there. The load is there. That is 2 ohm resistance load, RL. RL is 2 ohm. But instead of all the other elements that were there in the previous circuit, that you have replaced with one voltage source and one current source. One resistance. So you need only two things. All the other circuitry, you are representing all those things using two elements. One is a voltage source and one is a resistance. You don't require other things. Okay, so that is the aim. So we are starting from here, this circuit, and at the end we will be reaching this circuit. Now, why this is very easy? Because there is a voltage source and there are two resistances connected in series. So these two resistances connected in series, you can add them up. Okay, so 8 plus 2, that is 10. The amount of voltage that are being applied is 10. So 10 by 10, 1. So I is equal to V by R. So that is, I will be equal to 1 ampere. I will be equal to 1 ampere. So that 1 ampere current will be flowing through here. That 1 ampere current will be flowing through here. So if you know 1 ampere is 1 ampere current is flowing through this 2 ohm resistance, then you can find out the voltage. V is equal to IR. So 1 multiplied by 2, so 2 volt. So Vx, the voltage across this RL, will be 2 volt. If you know the current, if you know the voltage, what is the power dissipated? 1 ampere current, 2 volt voltage. So V multiplied by I, 2 multiplied by 1, that will be 2 watt. So 2 watt power will be dissipated across this 2 ohm resistance. Now, how to get that simplified circuit from this complex circuit? 3 steps. Okay, 3 steps are there. Broadly 3 steps are taken. First step, you have to find what will be the equivalent voltage. So VTH. Sometimes it is basically known as the Thevenin's equivalent voltage. This RTH, this is known as the Thevenin's equivalent resistance. So first thing, you have to find out what is the VTH. To find that, what you have to do? So the first step will be, you have to disconnect the load. Load was there in the circuit, but the first step, If you disconnect the load, this part will be an open circuit. It will look like this. Here the load was connected. Here this RL was connected. You have removed it. Now it is an open circuit. These A, B terminals are open circuit since you have removed the load RL. So the moment you do that, what are the conclusion you can draw? Okay, what are the conclusion? Can some current flow through this path? Will some current flow through this path? Let me know. So definitely some current will flow through here. Definitely some current will be flowing through here. Again, using KVL, you can find out how much current will be flowing through here. But will the current coming from this, will it get divided into two parts? Because there is a branching happening. So the current may go through this path, the current may go through this path. Will some current flow through this path or not? That's my question. Will any amount of current will flow through this 4 ohm resistor? Please let me. Please answer. Will any current flow through this 4 ohm resistor? Will any current flow through this 4 ohm resistance? Write yes or no. In the chat, write yes or no. Will any current flow through this 4 ohm resistance? Why? Akash is saying why. Yes, Pratik is saying no. Akash, why current will flow? Because there is open circuit. The first thing we have, what is the difference between network and circuit? Network is just interconnection of element, but circuit is where there is a closed path. That means through the closed path some current can flow. Here I have removed the load, and that's why the open circuit has been created. If there is an open circuit, no current will flow. So whatever the current was flowing, that will be flowing through this mesh or through this closed path. No current will be flowing through this 4 ohm resistance, because here there is no path through which the current can flow. There is no conductor. Okay. Yeah. So no current will be flowing through this path. So how much amount of current will be flowing through this? This is nothing but you should just discard this part of the circuit. You don't consider this part of the circuit. Okay. But how much current will be flowing through this path? That means some voltage is there, 30 volt. And these two, now if you are not considering this part of the circuit, what is the net resistance? 12 plus 6, 18 ohm. So 18 ohm is the net equivalent resistance. Two resistances connected in series. If you find out their value, it will be 18 ohm. Okay. So this is nothing but a voltage source connected like this. And in series, there will be a resistance. And in series, there is a resistance. This is of value 30 volt. And this is of value 18. Volt and 18 ohm. So what will be net current flowing? That is I. I will be equal to 30 by 18. This much amount of current, or it has been given here. So this much amount of current will flow through this 12 ohm resistance. The same amount of current will flow through the 6 ohm resistance, because there is no branching of this current here, because here you have removed the RL and you have replaced that with the open circuit. Okay, so the whole current that was flowing through here, this 30 by 18 amount of current will be flowing
Kalau dura, kamu, ang pada tungo.
Recording stopped.
Did sir leave the meeting?